Atomic structure, session 3, hydrogen spectrum, Rydberg equation, wave number calculation and ionization energy. This we'll study in this session. Hydrogen spectrum overview. Electron absorbs energy and jumps from lower level to the higher energy level, and higher energy level is always unstable, hence they will jump and return back to the lower energy level. This is called as emission of radiation. This leads to the emission spectrum. The energy difference between the lower energy level and higher energy level is calculated by using the equation delta E equals E2 minus E1. So that will be equal to h nu. So that will be equal to hc by lambda. Bohr's explanation of spectrum. The multiple transitions due to multiple atoms will be present. So different atoms will be going from lower energy to the higher energy level to the lower energy time level. At the same time, many atoms are involved in this. Therefore, multiple transitions will be taking place. Electrons return to the lower energy state and release energy. Spectrum consists of various lines of different frequencies. Energy transitions, delta E equals E2 minus E1. Using this, we can calculate the energy of the transition. That will be equal to Hc. That will be equal to Hc by lambda. And we are interested in a wave number. Wave number nu bar equals 1 divided by lambda. That will be equal to r into z square into 1 divided by n1 square minus 1 divided by n2 square. So this equation is called as Rydberg equation. It is also called as Ritz combination principle. So in this equation, Rydberg equation, R is called as the Rydberg constant. Its value is 1.09768 into 10 to the power of 7 per meter. Spectral lines. So in the hydrogen spectrum, the lines observed will be like this. Lyman series, Balmer series, Paschen series, Brackett series, and Pfund series. These are the 5 series observed in the hydrogen spectrum. Lyman spectrum, when n is equal to 1, n1 is equal to 1, then you are going to get in the UV region. Balmer series observed when n1 is equal to 2 in the visible region. Paschen series, when n1 is equal to 3, it is observed in the IR region. And Brackett series, n1 is equal to 4, observed in the IR region. And Pfund, n1 is equal to 5, it is observed in the IR series. Let us study what these things in detail. Series table. So here the first column is series, second column is n1, n2, and fourth column is region. Series, Lyman series, when electron jumps from n1 is equal to 1 to n2 is equal to 2 and higher. 2 and plus it is mentioned here. 2 and plus means it is n2 is equal to 2 or it may be higher. That is, it may be n2 is equal to 3, n2 is equal to 4, n2 is equal to 5. So probability that it can jump to any higher energy levels greater than 2. Then whenever it jumps back to the n1 is equal to 1, then you are going to get the series, Lyman series in the UV region. Similarly, Balmer series, n1 is equal to 2, n2 is equal to 3 and higher, observed in the visible region. Paschen series, n1 is equal to 3, n2 is equal to 4 and higher, observed in the IR region. Brackett, n1 is equal to 4 and n2 is equal to 5 or higher, observed in the IR region. Pfund, n1 is equal to 5 and n2 is equal to 6 and higher, observed in the IR region. Success of Bohr's theory. It explains about hydrogen-like spectra, that is, spectra of hydrogen, helium 2 plus, lithium 2 plus. All these will contain one electron. Second one, explains absorption and emission spectrum successfully. And third one, calculates radii, energy, ionization potential of the atoms successfully. It correlates the values of M, E, C, H. Limitations of Bohr's theory. It fails to explain fine structure. and second one is it violates Heisenberg's uncertainty principle. Third one, it fails for Stark and Zeeman effect. It fails to explain these effects. And fourth one, it fails for molecules and multi-electron atoms. Let us solve some problems. The first problem is find the frequency and energy of photon of yellow light whose wavelength is 530 nanometer. While solving the problem, we have to study what is given in the problem and what we have to find out. So accordingly, we have written this values here. So C, that is value C, that is velocity of light is 3 into 10 to the power of 8 meter per second. H is a Planck's constant, its value is 6.63 into 10 to the power of minus 34 joule second. We are using the formula C is equal to nu into lambda, where nu is equal to C by lambda. So that is 3 into 10 to the power of 8 meter per second divided by 530 into 10 to the power of minus 9 meter. So here in the problem 530 nanometer is given. So that is 530 into 10 to the power of minus 9 meter it becomes. So divide this, then you get 5.6603 into 10 to the power of minus plus 14 per second or hertz. And using this value, calculate the E. Energy E is equal to h nu. That is h is Planck's constant. Substitute the value of Planck's constant here, and nu. Nu means the above calculated value. Nu we are substituting here, and multiply this. You are going to get 3.752 into 10 to the power of minus 19. So shift the point, then you are going to get 37.52 into 10 to the power of minus 20 joule. This is the answer. Next, we'll go to the second problem. Calculate the wave number of first two lines in the Balmer series of hydrogen atom. RH is equal to 1.097 into 10 to the power of 7 per meter. So this problem can be solved by using the Rydberg equation. This is the Rydberg equation. Nu1 bar is equal to RH into 1 divided by N1 square minus 1 divided by N2 square. So in this equation. So here it is mentioned that calculate the wave number of first two lines. So that is for the first line we are going to calculate. This is the calculation. First line there is in the Balmer series means N1 is equal to 2, and the first line it should be N2 is equal to 3. So substitute N1 is 2, N2 is 3, then calculate it. You get 1.52 into 10 to the power of 6 per meter. This is for the first line. Next, for the second line, so N1 is equal to 4 and N2 is equal to N1 is equal to 2 and N2 is equal to 4. In this formula, you substitute, that is 1 by 2 square minus 1 by 4 square. You get the value 2.057 into 10 to the power of 6 per meter. So we have calculated the wave number of first two lines. Problem number 3. Calculate the wavelength and frequency of the spectral lines when the electron in the hydrogen atom jumps from 5th energy level to the 3rd energy level. So here using the Rydberg equation similarly, so Rydberg constant value we substituted here 1 by 3 square minus 1 by 5 square. So that is it is given in the problem 5th energy level to 3rd energy level. Accordingly we substituted here 3 square and 5 square. Calculate it, you get 7.80 into 10 to the power of 5 per meter. So you calculate the C. C is equal to nu into lambda, or nu is equal to C by lambda. Frequency we are calculating here. So frequency is C into nu bar. So nu bar means we calculated the above value here, substitute this above value. Velocity of light value we substituted here 3 into 10 to the power of 8 meter per second. This above value 7.8 into 10 to the power of 5. Multiply this, you get 2.34 into 10 to the power of 14 per second or hertz. Nu bar is equal to 1 by lambda. Lambda is equal to 1 by nu bar. That is equal to 1 by this value. It is 7.8 into 10 to the power of 5 per meter. This is the value of nu bar. And you get wavelength lambda is 1.282 into 10 to the power of minus 6 meter. So we calculated the wavelength and frequency. So this is the wavelength and this is the frequency. Problem number 4. Calculate the series limit for Balmer series of hydrogen spectrum. So here N1 is equal to 2 for the Balmer series, and the series limit is reached when N2 is equal to infinity. Substitute these two values in the Rydberg equation. This is the Rydberg equation. 1 by 2 square minus 1 by infinity is 0. Therefore, 2.74 into 10 power of 6 is the answer. Problem number 5. A spectral line in the Lyman series of hydrogen atom has a wave number 9.75 into 10 power of 6 per meter. Determine the transition responsible for this spectral line. For the Lyman series, N1 will be 1, N2 will be 2, 3, 4, etc. This is the Rydberg equation, and we are calculating here 1 by N1 square minus 1 by N2 square, that is equal to nu bar divided by RH. Nu bar value, this is the value, and RH value is this is the value. Substitute this and you get 0.888. 1 by N2 square is equal to 1 minus 0.888, that is equal to 0.112, and N2 square is equal to 9, N2 is equal to 3, and N is equal to 3, and N1 is equal to 1. Problem numbers 6, 7 and 8. Sixth problem is calculate the radius of the first Bohr orbit given the values of epsilon naught, h, m and e, that is z is equal to 1. We are using the r value, radius of the orbit is calculated using this equation. Substitute the values present here. Epsilon value, this is the constant, n square, that is 1 square because first Bohr orbit, and h is Planck's constant, this value is substituted. Z is the atomic number of hydrogen is 1. E, that is 3.141 is a pi value, and then E is the electron charge 1.6 into 10 power of minus 19 coulomb whole square into m, mass of the electron. So you substitute all these things, you get the value 0.530 Armstrong. Seventh question, calculate the velocity of electron in the first Bohr orbit. R is equal to 0.530 into 10 power of minus 10 meter. So we use the equation V is equal to NH by 2 pi mr. So N value, substitute this, H constant is the Planck's constant value 2, and pi value is 3.141, m mass of the electron is this value, and r radius of this is 0.530 into 10 power of minus 10. It is given in the problem. You get the value 2.185 into 10 power of 6 meter per second. Calculate the energy of the electron in the first orbit of hydrogen atom. So this is the equation used to calculate the energy. Substitute the values present here. Z value 1, m mass of the electron, and E is the charge of the electron. 8 into epsilon naught value is 8.854 into 10 power of minus 12 into 1 square into h value is Planck's constant value, and you are going to get the final value here. Revision. Bohr's model explains spectral lines like of hydrogen successfully. Energy change, that is delta E is equal to h nu, can be calculated. Nu bar is equal to rz square into 1 divided by n1 square minus 1 divided by n2 square, that is the Ritz combination principal equation, or it is also called as Rydberg equation, is obtained by this. And then series, different series like Lyman, Balmer, etc. we studied, and model success. So this explains successfully about the hydrogen-like atoms and matches the experimentally calculated values are matching with the calculated values. Limitations. It cannot explain the fine structure, Stark effect, and Zeeman effect.